Hello everyone, I am making a video to document the electronic tuning aid that I'm making for my Lunt hydrogen alpha telescope. All of the Lunt telescopes, to my knowledge, that have a pressure tuner have a very similar setup. They have the the tuning knob here, which has a pretty coarse thread on the inside. And there's a cap at the end of that right here that can be taken off. I learned that by looking at the online. They have a electronic pressure control device they sell, and it documents how to take this apart and install a replacement piston. So I discovered very quickly that this piston can be replaced, and I got to thinking, why not stick some kind of a sensor in here so we can get an understanding of what's going on inside of the pressure tuner. And that was pretty much the genesis of this project. I'll go over what I have here really quick and discuss why I'm building this. Right here we have it's a Feather M0, which is a Cortex M0 microcontroller. This is the EtaLon version that has the built-in SD card. I may or may not make use of that, but it was the only one that they had available at the time I made my purchase. These are nice because they have a built-in lithium polymer charging circuit, and that's kind of important because I don't really want to have any kind of wires attached to this, because as you know, this this knob gets turned while you're pressure tuning, and if you have a kind of a any kind of a cable coming out of here, it's just going to get all twisted up and it's going to be a nightmare to deal with. So I knew right away that anything I built had to be completely self-contained inside of this cylinder here. So in addition to the microcontroller, I also have it's a BME 280. It's a pressure, temperature, and humidity sensor from Bosch, and it's connected to the microcontroller over a SPI bus. In addition to that, I also have a six LED display, or 7 LED display rather. This is one of the NeoPixels from Adafruit as well. I kind of had a thought about what to use for a display. I wanted something that was small and could fit easily on top of one of these replacement caps that I would be machining. So it needed to be small enough to fit on there, and it also had to be bright so that it can be visible during the daylight. So this is what I decided to use. Obviously, there are some challenges in using a display like this to convey information. You got 7 LEDs, and trying to display numbers on that is a bit of a challenge, but I came up with a numbering system that kind of alleviates that. So I'll discuss that really quickly once I get the power hooked up here. So the battery, it's 350 milliamp hour battery. This should last for several hours. The idea is that you would charge the device up, and then disconnect the charging the charging cable when you go to use the scope, and it should be able to display the information. Now, the way this display works is that you can count the number of LEDs that are lit on the outer ring and count each of these as 1. So it'll light this one first to be 1, then it'll light the top and the bottom to be 2, it'll light these 3 to be 3, it'll light these right here in this box formation to represent 4, it'll light up these to represent 5, and then all of the outer ones lit would represent 6. The center LED represents 7, and then that's basically the 7th place. So then 1 plus 7 would represent 8. All of these in a line would be 9, and then this triangle formation would represent a 0 because it's 3 plus 7. If all of the pixels are lit, it would represent a decimal point, and that's more or less how I decided to lay this out. It's also color-coded depending on what date is being displayed, and I have a button that's not currently hooked up that allow you to toggle through the modes. Now, the theory of operation for this is pretty simple. The pressure tuners work because you have an EtaLon, which is really it's almost like a laser cavity. You've got 2 pieces of glass that are partially mirrored on the inside. They're very flat, and then you have some distance here. and any light that has a wavelength in this chamber that is double this distance. Basically, the light can come in, it'll bounce off the surface and bounce off here again. So anything that's got a wavelength that's double this gap will be able to pass through easily. And the formula for determining that that wavelength is equal to 2 times this distance d times the index of refraction of the media that's in here, which in this case is air. Now, in order to determine the index of refraction of the air, you need to know quite a few things. You need to know temperature, you need to know pressure, you need to know humidity, which this sensor can detect. So it's important to note that this is the vacuum wavelength of the light that's being passed, because obviously its wavelength will be different when it's inside of the airspace chamber here. But we're interested in matching this to the vacuum wavelength of the hydrogen alpha, which is 656.46 nanometers. Now, this distance d here is measured in nanometers, so the spacing here is going to be something that's close to half of this wavelength. So it might be something like, I don't know, 320 nanometers of spacing here. But obviously we can't machine things down to 320 nanometer precision, or close to that, within half an angstrom or whatever. So what they do is they use something like mica. They use a sheet of mica, and that can be cleaved at a molecular level and remain very flat. And then what they can do is they can use these as spacers between the EtaLon, measure it, find out if it's too thick, too thin. If it's one or the other, they can just cleave off a layer of it and keep going until they get a good match. And then at that point in time, they just snap this piece of mica, and then they use these as spacers in between the two pieces. And this is not necessarily going to be 320 nanometers. It's going to be some multiple of 2 times that number. So 2 times d, some multiple of 2 times d is what the thickness of these spacers will be, and it will allow the light to go through. The reason why I decided to build this project is that with the pressure tuner, you can get the tuning pretty much spot on just by using a camera. It's hard to do visually. You have to look at features such as filaments on the disk of the sun. Sometimes you can use the prominences to kind of judge it, but with the camera, it's relatively easy because you can look at the histogram coming off of the camera, and if you try to drive the peak to a minimum, as you increase the pressure, it'll start to drop, and then when you hit the correct tuning, the peak will start to swing back upwards. So the way this project works is it takes this value, you can calibrate it. You do this 4 times. You just set a button, or you hit a button once you've got this peak minimized, and what it will do is it will measure the current index of refraction that's being measured by the software, and it can calculate what this 2 times d is. So now you know that your spacing inside your EtaLon is some multiple of that value. And from that point forward, with that value, which never changes, you can use that to calculate what your EtaLon is currently tuned to for the vacuum frequency. And you can tell if you're red shifted or blue shifted from the hydrogen alpha line. So that is definitely an advantage, because in the scope design, you typically will have your tilt tuned EtaLon up front, and then you have your you have your objective here, and then you have a pressure tuned EtaLon right here. And this pressure tuned EtaLon, once you've tuned this pressure tuned EtaLon, without the double stack down there, once you have that tuned, It's tuned to the current conditions, which include temperature, pressure, and humidity. Now, the humidity is not likely going to change inside of the chamber, but pressure and temperature could very easily change, because once you've got this front tilt-tuned etalon in here, you're going to decrease the thermal load on this pressure-tuned etalon, meaning that the tuning is going to possibly shift. The challenge is that once you've put this on here and the tuning does begin to shift as a result of the cooling, it's really hard to separate the effects of these two etalons just by looking at the results through the eyepiece, because they're in series. So you can't really tell which one's red shifted, which one's blue shifted, which one's on target. So that's the goal of this project, is to quantify this value inside of this pressure tuned etalon and determine if you're red shifted or blue shifted, so you can get back to that mark. As the conditions change inside of the etalon, you can easily adjust and basically remove one variable, so then you can focus on the tilt tune. So I'm going to go ahead and power this up real quick. It'll start off by showing the count, how many times it's gone through the loop. It'll show the battery voltage. Then it will show the temperature in red, which shows up kind of orange here. Then it'll show the pressure in purple or violet. And then it will show the relative humidity in kind of a cyan color. Then it'll show index of refraction in white. And lastly, it'll show the vacuum wavelength in orange. So using the numbers I mentioned earlier, I'll just kind of go over this. Next time it runs through the loop, it'll be 1, because it starts at 2, or it does start at 1. I changed the code, so it starts at 1. So that was the battery voltage. Temperature is 26.75. This is in atmospheres. I'll read that next time it comes through. I am in Phoenix, so we are a little bit below 1 atmosphere here. So I'll go ahead and show this. I should probably slow this down from the camera, make it a little bit easier. So the next one will be the count, which will be 3. Actually, that's the vacuum wavelength. The next display will be the count, so that should be 3 times through the loop so far. So there you got that. Then it's going to show the temperature, or the battery voltage, 4.11. Then 26.65 was the temperature. Pressure is going to be 0.9, or I didn't catch that, 0.98, I think. And then index of refraction is 1.000255153. The 656.445 is the current vacuum wavelength that's tuned to. So it's currently at 445, which is below the correct value. So that's the gist of it. Like I said, I'll probably need to work on the display a little bit to kind of figure out something that's going to be a little bit more user-friendly. It's not terrible right now. I just need to slow it down. There's also a Doppler shift mode that I have set up in software where I can tell if it's red shifted or blue shifted and get an approximation of how far either direction. That's probably an easier tuning aid to use. And in addition to that, I can hook up a piezo buzzer and give some kind of audio feedback as well. So the next video I make for this project is probably going to be once I get the aluminum piston back from the machine shop and get the battery and everything fitted in there, and find out some way of dealing with how I'm going to pass the display wiring through here. That's actually a bearing in here at the top. The reason being is that the piston is going to be fixed with respect to the telescope because of the O-ring, but this will obviously turn, so it needs to have some kind of way of allowing the rotation to take place. So the cap that I use at the end here might not actually be fixed. It might just be kind of a dust seal of sorts. It'll probably rotate, or it'll probably remain fixed with the piston here. So it'll remain fixed with relation to the telescope while you tune it like this. So I'll probably have to make the shaft hollow so that I can pass the wiring through. There's only 3 wires needed for the display. It just needs power and 1 PWM pin, so it shouldn't be too much of a challenge to get that taken care of. So I'll work on drilling a hole through that once I get the piston back from the machine shop and get everything fitted. So hopefully this will turn out to be a useful project. I will post all of the code and design files online. Since all of the Lunt scopes use the exact same setup here, I'm hoping that I will be able to provide people with a project that they can follow if they want to adapt their scopes accordingly. So it'll work, with anything from the Lunt 50 all the way up to the larger scopes that are, I don't know, several $1,000s out of my price range. So anyways, thanks for watching. If you have any questions, comments, or suggestions, feel free to leave them in the comments. Thanks.